Hi, hello, welcome back to my video YouTube channel on um, cosmetics, beauty tips, cooking, and do-it-yourself. No, seriously. This is the third part on the tutorial on quantitative coding and complexity theory of continuous data. And as you may have noticed, we're about to leave the realm of a traditional tutorial and start to enter the realm of contemporary research on this important topic. So let me power up the slides. Here we go. Right. So, and let me start by giving you an overview of this part 3. First, we're going to recall the notion of polynomial admissibility, quantitative strength of qualitative admissibility according to Greitzer and Weihrauch for an encoding formalized as a representation, and then recall the first quantitative main theorem, quantitative strengthening of the qualitative main theorem, saying that continuous functions have continuous realizers with respect to admissible representation. And here we're going to obtain something quantitative. Functions with a certain modulus of continuity have realizers with certain modulus of continuity and vice versa. I'll explain the intentional later. But this is going to be the lead to the goal of this part 3, namely our goal is for an extensional and ideally also a tight, quantitatively tight version of this main theorem. And the approach we're taking here is an approach of multifunctions, multivariate functions, set functions, if you like, relations. We'll see that they cannot be avoided in computing with continuous data anyway. And there are many notions of continuity for such multifunctions, but none of them have the nice properties that we're looking for, in particular, closer and a generalized conception of restriction is essential for us. And we introduce a new notion, a heavily logic-based notion, and we will show that this notion indeed satisfies quantitative selection theorem. So there are many notions of qualitative selection theorems for continuous multifunction, but here we obtain what seems to be the first quantitative continuous selection theorem. But it has the important hypothesis that the domain and codomain of the multifunctions under consideration be ultrametric spaces. Now, if you recall, the Cantor space and the Baire space and the hyperspace that we have been considering as basic spaces are indeed ultrametric spaces. So that suggests that this is the right category of domains for generalized representation, just like for complexity investigation, just like equilogical spaces, according to Bauer and Berkedal and Scott, are the right category of spaces for generalized representation and computability investigations. So, and so we've closed this part 3 with a linear main theorem, a quantitative strengthening of the polynomial main theorem that we developed in part 2. But unfortunately, it's still going to be intentional in the sense that I'm going to explain them. So to remind you, in part 2, we've developed this kind of dictionary between qualitative and quantitative notions. And on the last line, we've already hinted at, but have not really expanded on why we believe that where equilogical spaces are the right category for qualitative investigations and codings, representations. Compact ultrametric spaces are the right ones for quantitative investigations for complexity considerations. And in the part 2, we've had developed the following polynomial main theorem that whenever we have two compact metric spaces with polynomially admissible representation with least moduli of continuity, then modulus of continuity of a function, modulus of continuity of a realizer gives rise to bound on the modulus of continuity of the function. That's reasonable. And observe that this bound here depends on the modulus of continuity of the realizer, and in addition, the modulus of continuity of one of the representation and the inverse of the modulus of continuity of the other representation, where this inverse now is to be understood in the sense of a pseudo inverse, because these moduli are in general far from injective and therefore not invertible. And there's a polynomial slack, a polynomial loss here, because we consider polynomially admissible representation, and it took us a really particular effort and care to design such a node to make sure that it is transitive and that every compact metric space has a polynomially admissible representation. So it seems difficult to improve that, to tighten that, to replace polynomial with, let's say, linear for the linear main theorem, and that's exactly the purpose of this section, part 3. And there's a converse, namely whenever a function is quantitatively continuous with modulus lambda, then it has a realizer whose modulus can be bounded and expressed in terms of this modulus, and again the modulus of the representation and the inverse modulus of the other representation and polynomial slack. Right. And so why is this intentional? Because it really, the statement of the theorem involves quantitative notions of continuity of the representations under consideration. So we're taking different polynomial admissible representations give rise to possibly very different connections and bounds between the function and modulus of continuity of the function and its realizers. So we don't want actually a theorem involving quantitative information about the representation, but we want that the notion of quantitative admissibility already captures all that, so that the statement of the theorem depends only on the properties of the space and not on the property of the representation, provided that the representation satisfy the quantitative admissibility condition that we're actually looking for and trying to devise here, right? That's one of the deficiencies, and the other deficiency is that this gap is what gives rise to this polynomial main theorem. Namely, if we start with, let's say, the statement from item B, we obtain with a function have a certain modulus of continuity lambda, we obtain a bound on the modulus of continuity of a realizer, and then plugging the modulus of continuity of this realizer into the statement from item A recovers a bound on the modulus of continuity of the function, but a much larger bound and much weaker statement, namely this statement here. So here's the modulus of continuity of the original function recovered, but there's this quantity which does not cancel, because this here is a pseudo inverse, right? Because modulus of continuity is not invertible in general. Same for here, this does not cancel. And there are these two polynomial slacks here. So one of the purpose of chapter 3 is, part 3 is to tighten these bounds, and the other purpose is to replace intentional with extensional. Okay, that being said, right, so what do we expect from an extensional quantitative main theorem? Instead of referring to properties of a representation, we want this is the theorem to refer to properties of the spaces, namely to their entropies, and then just say that there exist representations, and then define these to be quantitative admissible. There exists representation that imply the following bounds on the modulus of continuity of a function, depending on the modulus of continuity of the realizer, and depending on the entropy of the space under consideration, and conversely, bound on the modulus of continuity of the function give rise to bound on the modulus of continuity of a realizer depending on that modulus and depending on the entropies of the spaces. And we want these two statements that now do not depend anymore on quantitative properties of the representation. We want these statements to be tied in the following sense, that if we first apply item A, let's say, and then item B, that means we consider the composition starting with modulus lambda, obtain a modulus bound on the modulus kappa, plug that into the other statement, then we hope to recover, or at least not to lose too much information about lambda, to not get something much larger, and similarly the other way around. That's our hope. That's what we want, but spoiler alert, in this chapter 3 we're still not going to fully achieve that. But what we will achieve is this intentional but linear main theorem, and the motivation and the approach to get there is the study of multifunctions. So why multifunctions? One motivation is by considering the conditions that we imposed in our notion of polynomial modulus of continuity, and attempt to tighten that while still making sure that every compact metric space has a representation that satisfies these tightened conditions. And one condition is about this polynomial reduction from one representation to the other. And we can conveniently, this is the condition, and there were some quantitative conditions about the least moduli involved, least modular of continuity of this representation, and this representation. And but now observe that we can reformulate this strange condition by formally putting psi inverse to the left. Then the result is this condition, psi inverse is now on the left. And that basically, observe that psi inverse, of course, is not a function, because representation in general is not at all injective. So this is a relation. This is to be understood as a composition of two relations, whereas the right-hand side, the realizer, is still supposed to be a function, namely a selection of that relation on the left. And we want to derive some quantitative bound on the modulus of continuity of such a single-valued selection, depending on the modulus of continuity of the multifunctions involved. That's our goal, our motivation for why we introduce notion of continuity for such multifunctions. So why multifunctions? Well, in ordinary function represent a class of decision problems or computation problems, where there's an argument x, an input, and there's an answer y, and that's a unique answer as given by this function problem. We ask how to compute that, but there are many applications where the answer is not necessarily unique, like the way we talk, right? Usually many possible answers. And we're in the computational version of that problem, we're only supposed to answer to provide any feasible, any admissible answer y. And this is a search problem, and it is captured mathematically as a multifunction. So that's this oxymoron that there's multifunction are sometimes called non-extensional function, but yeah, well, every function is extensional by, that's the whole point of having a function. So I'm going to try to avoid that oxymoron. But such multifunctions are actually unavoidable in real computation, has been known for a long time. So here's an example, namely this sine function with this overlap here. It's an overlap that makes this sine function computable. It's a multifunction in the sense that for arguments that are close closer than epsilon to 0, both possible answers, both possible return values +1 and -1 are allowed, are feasible um, in this multifunction. And that's what makes the multifunction computable and have a continuous realizer, this kind of overlap, right? Non-uniqueness, ambiguity. Whereas if we replace epsilon with 0, then this function is not computable anymore. It does not have a continuous realizer because, well, here locally everything is fine, same here, right? But here at this point, if we change the argument a little bit, it will switch and definitely switch to +1. But if we then change a little bit back, then it must be -1. So there's no way to do that continuously. But when there's a overlap, then we can really harness the multivaluedness to get a continuous realizer. So the baseline here is we need to consider multifunctions. So let's do this. And let's first start by formalizing what is a multifunction. There are many mathematical formalizations, for instance, as considered as a relation. That's one way. Another perspective is of that as a set-valued function, a function whose codomain is a power set. Usually, actually, it suffices to consider space of compact sets, like, for instance, Hausdorff space. And by allowing multifunction, many of the concepts we've considered so far actually become more convenient, and that's the reason, right? We want things to be simple and convenient. So to demonstrate that, let me first remind you of the notion of a realizer extends from a realizer of a function to realizer of a multifunction. Namely, it's this very condition. It's that this diagram commutes only that now here this function is multivalued. But observe that the realizer itself is still required to be single valued, and this will later require us to cover up a selection theorem to make sure first we do all the operations just plainly symbolically using these inverses of representation, and then finally make sure that there exists a realizer selection in this multifunction whose modulus of continuity is close to the modulus of the original multifunction. So this is kind of the motivation for where we study continuity for multifunctions. Right. So let me remind you that the conditions of a realizer and the condition of a continuous reduction can easily and conveniently be reformulated in terms of compositions of functions and multifunctions. So that's actually to make things simpler. Right. So what about continuity for multifunction? Well, there's a tendency in mathematics, understandable, to consider as a multifunction either as just a relation, so it's not a function after all, so fair enough, or as a function whose values are actually elements of a power set, or let's say element of the Hausdorff space of compact non-empty subsets. We will only consider multifunctions that have compact values that are compact themselves. So, but these both conceptions do not really capture the essence, the idea of a search problem. Namely, the important aspect of a search problem is we don't require that all possible answers ever be given by an algorithm. Algorithm just can give any answer, and if it always omits some answer for whatever reason, then it's still going to be considered as a solution. Whereas when considering a multifunction as a set-valued function, then really there's the value is the set, and there it is. So it's a subtle point, but this not necessity to output all possible answers. That's what captures the multifunction, and that's what prevents us from considering a multifunction just as an ordinary set-valued function. Also, there's the issue with the continuity, right? So We want to have a correspondence between multifunctions that are continuous in a certain sense to be developed and that have a continuous realizer. And well, if we consider the codomain equipped with a Vietoris topology, then there is a selection theorem, then there is such a relation, but it cannot be made quantitative because a Vietoris topology is only a quasi and pseudometric. Same the reason is that the host of metric on the space of, let's say, compact valued multifunctions. This, for instance, makes this sine function discontinuous. But let's have a look at what's happening here. So whenever the argument x is here, then the return value is just a singleton, right? Here the return value is a two-element set, and same here. So that seems superficially to fit into this conception, but in the host of metric, going from here to here makes the distance jump. So from here, where this to here, where this upper point starts, that's where something jumps. So it's discontinuous. There is, to be fair, there's a way to make it continuous by removing the endpoint so that this is kind of an open set. But again, recall that we want to consider only compact multifunctions for reasons of similarity with the single value case. In the single value case, every continuous function with a compact domain actually is compact in the sense that it has a compact graph. And for multifunction, we're going to impose that condition to have a compact graph. Right, and the Vietoris topology, lower and upper, also don't satisfy this. Host of metric don't satisfy this. So what are we going to do? We're just going to come up with the notion of continuity. And this notion should satisfy a new additional closure property in addition to the usual closure properties of ordinary continuity. Among those closure properties is that, for instance, the composition of continuous functions should be continuous. And here we want, and the restriction of a continuous function should be continuous. Here we have a different additional notion of restrictions, so let me point that out for you. So in the perspective of function problem, restriction means making the problem easier, right? Because there are less possible inputs to consider. Let me illustrate that with this image on the next slide. Here's the image, yes. Namely, so the light gray area is kind of a restriction of the dark gray area in that here on this gap, it doesn't the light gray area doesn't really expect or suppose any possible answer. So the domain of the light area is smaller than the domain of the dark gray area. The light area is a restriction. But there's another notion of restriction that also is nicely exhibited here, but that's new to really multifunction, namely having a larger range. So if you consider, for instance, this argument, there in the dark gray area, there's only a small possible range of answers, an interval here. But if we consider the gray multifunction, there's a much larger range of possible answer, which should make the problem at least not harder, but maybe easier, right? So if we want to have a notion of restriction that also captures both notions of becoming easier, and that's a little bit subtle because, or can easily lead to confusion because the light gray area has a larger range. So what would we call that restriction? But here we're following terminology of Gleis-Weyrauch, that restriction captures both, and thus restriction is exactly what should make a computational search problem at least not harder. And also we want the class of continuous function to be closed under these both conception of restriction, having a smaller domain and having a larger range of possible values. And this is unfortunately not satisfied by the arguably most popular notion of continuity for multifunctions, namely upper or lower hemi-continuity, is not closed under restriction in this new sense. So we have to abandon this notion and come up with our own notion. That's another indication of why the conception of as a set valued function is not a suitable one, because again, this is not closed under taking composition. Good, right, and like with continuous function, remember the classical theorem that a continuous function with compact domain is continuous, is compact, has a compact graph. We want the same to hold for multifunctions, and but we cannot derive it, so we're just going to impose it as an axiom in a sense. Good. So now, what is about quantitative continuity for such multifunction? To this end, please recall the classical notion of a modulus of continuity of a function. Maybe that's a mapping from natural numbers to natural numbers that satisfies the following property: when x and x prime, the arguments, are sufficiently close, namely closer than 2 to the minus mu of n, so largest values of mu correspond to larger values of y. Um, um, then we want the same to have for the values. So if x and x prime are sufficiently close, then also the values y and y prime should be sufficiently close, and this is captured by this function on natural numbers. The closeness here meaning 2 to the minus mu of n, and the conclusion says distance up to 2 to the minus n. So this is capturing the epsilon delta criterion of continuity. And a different way of rephrasing that equivalently is in terms of balls, closed balls. So x prime should be in the closed ball around x with radius 2 to the minus mu of n. Then y prime is closed, namely the closed ball of radius 2 to the minus n to y. And this is all, for your convenience, terminology for closed balls, where here the radius is restricted to negative integer powers of 2. That's what we're considering from modulus of continuity and from entropy, so we're going to stick to that here. And there's another way of reformulating this modulus of continuity condition, by the way, right? Since this is still defined only for functions, the values y and y prime are uniquely given equal, so no multifunction here. But of course, our goal is to generalize it, and one important question to ask here is how do we quantify over the values y and y prime in g of x and g of x prime? Should we quantify existentially, or should we quantify universally? And both have been considered, for instance, by Vasco Podka and Peter Hertling in 1994. And so we're going here to stick with existential quantifiers for a reason that will become apparent in a few minutes. So the other thing I'd like to discuss here is that it suffices qualitatively to require this only to for all sufficiently large n, because that's where the continuity really happens, with large n meaning small distances. It's a local property. One can also impose the same condition only for an n that are elements of a arithmetic progression, multiples of some certain element n0. And these are all qualitatively equivalent. Quantitatively, there's a little difference. Namely, in this case, we first have to get to the first meaningful value of n. And here we may need to climb up to the next larger multiple of n0 on the arithmetic progression, so that we kind of could lose an additional offset in the argument of up to n0 minus 1 to recover the original notion. So there's a difference, qualitative, but it's a small difference. That's a message here. And I've explained and showed this to you because this is our starting point for devising the generalization to multifunctions. So here you see basically the same expression, but now for multifunction. The quantification over x prime is replaced by quantification over x1, and where x prime should be close to x, similarly x1 should be close to x0. And the conclusion is that there exists a y, remember, existence here, that is sufficiently close to y0, and that now belongs to the range, to the set of possible values. So in a multifunction, there's no unique answer y1, y prime, but there are many possible answers, and there should be one that is close. That's the condition, but that's not entirely the end of the story. First thing we need to consider is we also need to quantify over the argument x0 and the value y0. Of course, this is only about x1 and y1 in relation to x0 and y0. So we'll quantify over both, over x universally and over y still existentially. And then there's this quantifier about the step width of the arithmetic progression that is arbitrary but constant. And right, so that's almost where notion of continuity for multifunction. Observe that for an ordinary function, this is really just our notion of a modulus of continuity. So this is going to be a generalization, but we're not there yet. We're going to add another condition, which is basically of the same form, only that it now relates. Suppose that if x2 is sufficiently close to x1, then y2 is sufficiently close to y2, y1. So that's kind of iterating, applying the same principle again, but to the next pair of arguments and values. And there's another quantification over or different consideration of the parameters, integer parameters to the moduli of continuity. So this is a next level of logical expression as the formula capturing what we conceive to be quantitative continuity of multifunction. I'm going to explain that with examples on the next slide, but let me just for now here continue. Of course, again, this is not the end. We're going to require the same condition also for x3 in relation to x2 and for y3 in relation to y2 and so on. Up to the xk in relation to xk minus 1 and yk in relation to yk minus 1. And we're going to do that actually for every number k for reasons that become apparent on the next slide. So this is now our formalization of quantitative continuity of a multifunction, compact multifunction with modulus of continuity mu, not necessarily optimal modulus of continuity. And let me stress again that it's easy to see that these conditions actually all boil down on kind of falter, become trivial when we're dealing with a single valued and ordinary function, and they become just the ordinary definition of continuity for functions. So it seems like a generalization, very subtle, but the important one. So some of the nice properties that this notion satisfies is that it, yes, as I said, it generalizes modulus of continuity for single valued function. It is now closed under both kinds of restriction, smaller domain and larger range, which like hemi-continuity, for instance, was not. That's the kind of easy to see, so I'm not going to expand on that and leave it for you as a homework exercise. This is closed under both kinds of restriction, and is closed under this composition of multifunctions as I just defined it, provided, and this is a subtle but important hypothesis, provided that the modulus of continuity is strictly increasing. So if you wonder why do we impose that hypothesis, just figure it out, close under composition, then you see where and why we need strict increasing moduli only. Okay, now we really have our notion of quantitative continuity for multifunctions, and we can consider some examples and approach our um, technical main result is selection theorem, quantitative selection theorem in multifunction. So what are the examples? So in the following, we're going to consider total multifunction G from X to Y. And here for your convenience, let me remind you of the definition of continuous reduction. And now we have a notion of a modulus of continuity for multifunction and the notion of reduction. Reduction that goes as follows. X is a reduction from X to Y. If X is A, has the same domain as the original multifunction, so original multifunction is total, then so must G be. The second condition is that it satisfies this very continuous reduction property in its original formulation. No, not the continuous reduction property, but being a restriction, right? So here G is multi-valued, the right-hand side is single-valued, and total, right? So that's implied here. That means that's what people call a selection. We want a continuous selection. So yes, here's some examples. So here this multifunction kind of is continuous, namely it suffices for us to consider the dark gray area, and even maybe just some line through the dark gray area will be kind of a continuous reduction of the original problem. So that's good. Well, let's consider the sine function, which seemed a little bit strange, right? And to recall that this sine function is discontinuous when the parameter is 0, and indeed it violates this continuity condition. So let me expand on that. Consider x0 here to be that very line. Now we're going to play the game and let the machine evaluate this expression it has just passed on this sine function, and then we change x1 to be very close to x0. Then either if we move x1 a little bit to the right or a little bit to the low, then also enforces a change in the value, and that's exactly what makes up for the discontinuity. Namely, technically this condition is violated. In this case, y1 must be here. In this case, y1 must be here. They must be distinct, but on the other hand, continuity requires them to be close, so that's what fails here. Continuity, what now if we add this epsilon slack overlap, then suddenly the sine function does start to satisfy this multifunction. We just need to make sure that the n's are sufficiently large so that there's no such sequence of parameters that could kind of climb off the cliff here. And that's certainly true if we use this above notion and if we use the above modulus of continuity. So for the sine function, this notion seems good. But if we now consider this other multifunction, then things start to become sour. Observe that this multifunction is not computable either. Why is it not? Why does it not have a continuous realizer? Because if we start with x being this value, then moving x a little bit right or left makes a huge difference. So what you see here is basically the characteristic function of the irrationals and the rational numbers, and same here. And that's of course a totally disconnected function. And in our setting, it means if we choose x0 to be this value and x1 to be here, then we must consistently choose this kind of the upper value. We must never pursue to these values here. And same here, when x0 is here, then we must consistently for x1 like left, we can only choose this as possible answer, as possible y1 here. So the baseline is this multifunction satisfies these two lines, but it is not computable. It does not have a continuous realizer because of this the characteristic function of the rationals and irrational is so highly discontinuous. So what are we going to do then? We're going to add this new line, remember? And now it's easy to verify, but I want to leave it to you, that this multifunction violates this new condition, which brings it into agreement with the fact that this multifunction does not have a continuous realizer. And here we can iterate this construction. We can play a game, keep devising more and more complicated, compact multifunctions that satisfy longer and longer initial segments of this sequence of logical expression and satisfies an arbitrary large initial segment, but not the k plus first one. So there's kind of a proper hierarchy here, and we require all infinitely many of these conditions to hold. Well, every finite condition to hold for every integer k. Good. So that wraps up a part about multifunction and continuity of multifunctions. Now we can state, now we're ready to state the technical main result of this third part, namely a selection theorem, a quantitative selection theorem, and you're welcome to look up the archive preprint for this statement, this selection theorem. This is really a very good highlight, and it depends on the domain and codomain both to be actually ultrametric spaces, right? As because as you recall, the overlapping sign function satisfies this technical notion of continuity, but does not have a continuous selection. But when the ground and codomain are ultrametric spaces, then according to this theorem, it does. Namely, whenever we have a total compact multifunction from D to E that satisfies this complicated logical expression for some strictly increasing mu, remember we need moduli increase strictly, then it admits a single valued selection, which is also not just continuous. There are many continuous selection theorems in analysis, but we also derive a bound and the modulus of continuity almost type, because there's always this constant offset that may, for instance, or may not be the right, this constant offset that may or may not come from the n integers parameters n to be restricted to this arithmetic progression. Okay, so I will not prove this selection theorem here. You can find the proof in the archive preprint, but we're going to apply it because now recall why we did all this thing. We wanted a intentional quantitative main theorem, and here we got it. Namely, if we have compact metric spaces whose representations are just the way they are, they must have domains, compact ultrametric spaces. Actually, it's no loss of generality as we require here them to be total representation, because if they're partial but still have compact domain, then we can just restrict to this compact domain, hence this form in term compact ultrametric space. So suddenly the representation is total. So it's no loss of generality. And let's consider increasing modulus of continuity of these two representations. And this is now where the subtlety starts, moduli of continuity of the inverses of these multifunctions. As you recall, the inverses of representations are not not functions in general, but they are multifunctions. And since we have finally come up with this formal notion of continuity, that's why what allows us to really write down that condition and to harness it. Okay, good. So for your convenience, let me repeat you what it means to be a realizer. And then the statement is the following. if the multifunction f has a realizer which is just continuous, remember realizers are single valued, with modulus of continuity kappa, then it is actually, there's a complicated expression, a bound on the modulus of continuity of the original function, namely it is continuous with respect to this complicated expression. So that's the first half of our main theorem, and the second half is kind of a converse. If the function is A, compact, we know we need this hypothesis, and B, if it is continuous with the modulus of continuity lambda, then it has not just a continuous realizer, as Kreutz and Weyrauch would predict, but it has a realizer which in turn admits a bound on a modulus of continuity, namely a bound considered in the following way. And here we only have this kind of slack, right? So this is some constant additive to the argument, and that's very little slack. Well, that's why we have been doing this all the time, right? And that's easy to see. One direction, if we have a continuous realizer, then the original function is also quantitatively continuous. Why is that true? Well, because of this property that the modulus of continuity of a single function will be a restriction of the modulus of continuity of a previous larger function, possibly. Okay, so that direction is basically follows from uniform continuous multifunction now here being closed under composition with the moduli of continuity forming composition in the converse direction. The interesting new and highly difficult part is item B, which says the converse. If we have a function which has a certain modulus of continuity, then it has a realizer with certain continuity properties, namely this continuity property. So let me spell that out for your convenience. There's this modulus of continuity of the original function, right? And then there are two moduli of continuity, like in item A, this one and this one. These are the properties, quantitative properties of the representations under consideration. And then there's a shift, but the shift is much smaller than the shift that we suffered and experienced when we talked about the polynomial main theorem. Namely, it's a constant shift, whereas polynomial had a kind of a polynomial kind of slack here. Okay, that's our intentional quantitative main theorem. It's still intentional because it depends on properties of the quantitative properties of the representation, but it's already an important improvement, because using that intentional linear main theorem, we can now derive the linear real case quantitative main theorem that I already introduced and advertised at the end of chapter 2 regarding the sign-digit representation. So to remind you, the polynomial real main theorem due to Carré-Coe characterizes real functions, let's say unit interval to the unit interval, with a modulus of continuity that is here supposed to have a certain form, namely a polynomial, translate the argument, then put that as value into the original modulus of continuity, and then again apply a polynomial modulus of continuity and apply all these in such a way so that we get this kind of slack on the argument, polynomial slack and the value. And then the polynomial main theorem to the Carré-Coe that this has a realizer. I'm just going to say delta realizer for convenience, whose modulus is basically the same, right? If you see that here, yes, it's the same modulus. Well, it's not the same modulus, but it satisfies a similar bounds. So that seems like a great theorem, but it has this polynomial slack here and here. And observing that the Cantor space C is an ultrametric compact, so we can apply our new quantitative May theorem and take into account that the sign-digit representation has a linear modulus of continuity when considered as a mapping from that Cantor space onto the real unit interval. And finally, yes, and it has a compact domain. And this is a non-trivial part of this example. Consider the inverse of the sign-digit representation, which is maybe used not very rarely, but it turns out that this also has a linear modulus of continuity. The inverse, the multivalued inverse from the 0-1 interval to the C, the Cantor space, it is a not trivial mapping. So now I didn't prove that, so don't worry if you don't understand why this is the case. It's subtle, but now we can throw things together with this intentional linear main theorem and replace mu and mu prime and nu prime model of continuity of the inverse of the sign-digit representation, all with linear, and then we get the following characterization that real function has a linear modulus continuity linear slack, apply some modulus, and then again apply linear if and only if it has a sigma realizer with the same modulus. So here, as opposed to the polynomial real main theorem, the loss we suffer here is only linear, not polynomial, when moving back and forth. But this is specific to the sign-digit representation. We've been trying to generalize such things to other more abstract spaces. And that's why we're doing all this here. So I mean, we still have this vision with this linear main theorem. Well, this is still only applies to the real case where we already know so much. And this is only this intentional linear main theorem in that it depends on modulus of continuity of the representations and of their inverses. And we still don't know very much about the modulus of continuity of such representation and their inverses because they don't cancel. That's a subtle but important observation. More precisely, we want, remember, one goal is to get a modulus of continuity as small as possible according to Steinberg's lemma. But if we do that, and my student Dr. Lim has done that in his master thesis, then we might kind of spoil or increase the modulus of continuity of the inverses of this representation. So it's still intentional. It still depends on properties of the representation rather than only on properties of the space under consideration. But this is exactly what we're hoping for and what we will continue to work on. So this is really ongoing research. What we hope is a quantitative main theorem of the following form. If we have compact metric spaces with certain entropies, then we want to be able to relate quantitative continuity, modulus of continuity of functions, or actually multifunctions, to modulus of continuity of values, namely via the representation. And the statement should just say that there exists such representation, such that having a realizer with certain modulus translates into a function itself having a certain modulus that depends on these parameters, and vice versa. A function having a certain modulus translates into a realizer having a bound like this. And we want this to be tight so that if we proceed from A to B and from B to A, we don't lose too much. We want, this is what is said here, proceed from B to A, then we want that to be almost tight to almost recover the natural modulus of continuity. And that's what we did not achieve in the previous notion from part 2, where there was always this polynomial slack, for instance, that could never be removed. Okay, thank you very much. That's all for this part 3. So to summarize, we've talked about the relevance and importance of multifunctions, where they're not considered as relations, where they're not considered as set-valued functions. We've discussed various classical notions of continuity for such multifunctions and a new quantitative notion that has the additional benefit of being closed under this new notion of restriction. And then we've introduced, but we did not prove, our new quantitative continuous selection theorem for multifunctions between compact ultrametric spaces. This is what you can find in the preprint with my student Duncan Lim. And we've discussed the linear main theorem in the real case, so there's still a restriction, but it is, I think, the tightest form of main theorem that I've ever seen, including the work of Carrico. It's still intentional, so our hope is to remove extensional with just to get rid of that, and at the same time um, meaning that the theorem should be expressed in terms of quantitative properties of the spaces in terms of modulus of continuity. And yes, there will be a part 4 of this tutorial where I talk about complexity of higher types, where I recall and explain why we consider these strange hierarchies of one Lipschitz function either onto the unit cube or onto the Cantor space, and also discuss models of computation for these higher types, for these higher basic types. Good, thank you, and the end.